morning from the almost sunny Copenhagen. Welcome to the eTraining Enhancing Energy Efficiency in East Africa, hosted by the Copenhagen Center on Energy Efficiency. My name is Aris. I'm working as a program officer at the Copenhagen Center, and I will be the moderator for today's eTraining. A couple of things before we move to the main content of our eTraining. The eTraining is going to be about 100 minutes long, including time for the Q&A at the end. In case you cannot stay until the end or want to get back to our presentations, all the materials and the recordings of the whole eTraining will be available online in a few days on the Copenhagen Center's knowledge management system. And we have many other webinars and training information over there. Have a look. Now, as always, before we start discussing about today's eTraining, I would like to inform our attendees one more time that we comply with the General Data Protection Act, also known as GDPR. This means that your personal data, such as name, email, workplace, is safely processed and stored, and all of your rights pursuant to the GDPR are respected. You have full access to the data are being processed about you, and at any time you can request that inaccurate data be deleted or rectified. For access or further information, please contact the people that are presented here. Now, a few things about the Copenhagen Center. The Center conducts research and advisory activities in the field of energy efficiency and serves as energy efficiency hub for the Sustainable Energy for All initiative. The Center has an established network of global, regional, and national partners with a broad range of stakeholders to help accelerate the implementation of energy efficiency activities. I would like to briefly introduce the speaker of today's eTraining. We will start with Rahul. Rahul is a senior expert at UNEP-BTU Partnership. His role involves identifying short and long-term technical and financial potential of energy efficiency implementation measures. Then we will continue with Clara. Clara is a postdoctoral researcher specialized in the climate-conscious transformation of the building sector. And then we're going to have Xianli. Xianli is also a senior economist at the UNEP-BTU Partnership, and her work focuses on analyzing and designing enabling policies and programs for energy efficiency improvement and climate change mitigation. Now, before we go to our first speaker, I've been asked to conduct, as always, as we do our training, with just a few poll questions in order to better understand our network. So the first question is, do you work on operations, maintenance, or anything related to HVAC systems? And you have two options, yes or no. So I'm going to give you a few seconds to respond to that question. Okay, let's see the results. And as we can see, 43% said that they responded yes, and 57% responded no. Now, let's go to the next question. And the question is, do you know how to evaluate HVAC components' performances? As always, I'll give a few seconds to have some time to respond. And the results of these questions, okay, 80% responded no, and only 20% responded yes. Now, let's go to the next question. Rate your technical know-how on HVAC systems. And here we have four options: new, moderate, and expert. And let's see the results. Okay, 34% categorize themselves as new, 64% as moderate, and only 2% as experts. And let's go to the final question before we go to Rahul's presentation. And the question is, do you work with or are you associated with water utilities in your region? And as always, you have two options, yes or no. Okay, let's see the results of the specific question. Okay. 67% said no, the majority, and only 33% yes. Now, before we go to Rahul, I just want to mention that you can send us your questions during the presentations using the dedicated icon, as always, and we will do our best to answer as many as we can at the end. Please do not forget to mention the name of the panelist that the question is for. And with that, I would like now to give the floor to Rahul. So Rahul, the floor is yours.
Good day, everyone. Welcome back to the Energy Efficiency Training Program. Last week, we talked about main building envelope components along with some subsequent energy efficiency actions. We also covered some key steps to conduct energy audits and adopt energy managements for the buildings. Today, we will be covering some 4 interesting topics. It's slightly a longer session, but yeah. So I'll directly dive into the first topic of the day, that is energy efficiency in HVAC systems. We would start with a brief look into the status, and then move forward. The subject is again, it's definitely not justified to cover it in within 30 minutes, but I'll try my best. And so since time is limited, I'll be cruising through these slides. And hence, I'll be covering the application-based or experience-based important aspects. Most of the theory will be anyways available with you with all over the internet and different resources and research papers. If you are, however, further interested in knowing more about the topic, you can reach out to us. The pulse of the presentation will move from easy and simple in the beginning to a bit more technical and complex in the end. But looking into the polls, I think quite a lot of the attendees today are aware of what HVAC systems are, and they are quite. I mean, most of them are also working in the sector. So yeah, if you find it too easy or too simple, you can please let me know, and then we can see how we can discuss further for any specific topics on HVAC systems. So the presentation would be something like what we would be covering: what HVAC systems are, why do we use them, when do we use them, where, and how exactly we can improve the efficiencies of the systems. So, I mean, this is quite a straightforward topic here. HVAC, that is heating, ventilation, and air conditioning systems. Remember, you need to focus here that it refers to a system. That means it comprises of not just heating or cooling equipment, but also, the auxiliaries associated with it. It could be fans, blowers, cooling towers, air handling units, pipelines, circulating pumps, and all. If you further get into the details, into the system level, you have several more components that you may have to deal with depending on the type of the system that you have in place, or type of usage you have in place. Some of the components you might come across are listed here. And each one of these components their operations, they can actually impact the way your entire HVAC system performs. I mean, you can have a look into individual components later on, but for example, I can just give you you take air filters. Air filters you come across in air handling units, mostly where there is air intake. And let's if the air filters are choked, then you might be having pressure imbalances in the system. You might be having some disturbances in the system. There is no sufficient airflow into the systems, which can create or initiate some inefficiencies in the entire HVAC system operations. Now the question can be, why do we need HVAC systems, or why do we have to discuss or give importance to these systems in first place? I mean, it is obvious that the major investment generally goes towards the envelope when you come up with a new construction, and then so this is something where you need to ensure that you avoid any room for errors, because later on rectifying it would be a bit more complex and expensive. And the next best thing that comes out is the HVAC systems, which with respect to the investment levels. This is something I would want you to focus on, which will give you a better, quite a clear idea on how or why the HVAC systems are given a lot of importance. Please note that this pie chart, what I'm representing here, is mostly based on the actual energy efficiency and energy audit studies for over a period of 10 years. The first chart on the left shows you the percentage distribution of total number of proposals that come up among the different components. We see that the total number of energy conservation proposals that have come up from the energy audit studies of the buildings, we have the highest number for HVAC systems. The second chart, the one in the center, again, it shows percentage share of each component in the total energy savings that were estimated and achieved. Once again, we see HVAC systems showing the largest chunk of energy savings. And depending on the type of building, the second position can be the boilers or the steam or hot water generators or electrical systems or even lighting systems. On the last or the third chart on the right, we see about 57% of the total cost savings that are achieved are again from HVAC systems. So by now, we have understood. We can understand that why there are so many cooling or heating related programs and projects all around the world, because there is a huge potential and achievable energy and cost savings, and this is tried and tested. There's not much about asset analysis or estimations and all, but it's more about based on real data or real achievable data that these things happen. So what we see in our day-to-day activities is a mix and match of the requirements here, the mentioned requirements here. So basically, you have exclusive heating and humidifying and quality control under air conditioning. Then there is some exclusive refrigeration, where mostly it is used for industrial segments or food and processing industries. And then you have a mix of both these, wherein you have this cooling and dehumidifying operations in your air conditioning systems. So application-wise, you can use it for comfort or space conditioning, but that's like your office rooms, your conference halls and buildings, shop floors and industries and all. It can also be used for process cooling in industrial applications to maintain bearing temperatures or maintaining reactor or heat exchanger temperatures, critical storage cooling and all. Coming to the brine systems, it is mostly for critical applications where instead of water, they use brine solutions for circulation and temperature maintenance. You can find it in pharmaceutical industries. The slides from here would be talking about three different questions. That is how the system works, how do we assess the performance, and how to save energy. So, this most of you are aware of. Anyone who is from the mechanical engineering background or chemical engineering background should be aware of that. The HVAC system is generally classified into three sections. It could be a vapor compression system, a vapor absorption system, or evaporative cooling system. We will be first talking about the vapor compression system. I just want to run through these slides, giving a brief fundamentals of how the system works. So you have two fundamental concepts here. One is an evaporator and one is a condenser. This is for a system, basic split AC is what you see day to day in your office rooms or in your homes and residential areas. So you have an evaporator which cools down the indoor air with the help of a refrigerant, and you get the cool air into your system in your room again. And then you have a condenser where the refrigerant rejects the heat into the outside atmosphere. This is the outdoor unit, wherein if you go and stand near this outdoor unit, you would find some hot air blowing towards you, right? That is nothing but the refrigerant rejecting the heat that it has absorbed inside. It is rejecting the heat into the outdoor environment. And these are the different types of air conditioning units which you come across on your day-to-day life. Now we would be looking into the air-cooled systems again, which are slightly larger. Again, the fundamental concepts would be remaining the same. That is, you have an evaporator and a condenser. In order to cater to the larger areas, there would be no direct contact of air to the evaporator. Instead, you have water here. So we saw direct contact of air with the refrigerant coils, but now you see uh, the water which is cooled here will be supplied to the air handling units or the fan coil units into your building. This is generally for larger buildings which is applicable. And the condenser side is, again, since it is air cooled, it's still air that is there. But the difference from the previous slide systems and this system is that this is a larger capacity, so you will be having larger banks of fans which will be trying to enabling the refrigerant to reject the heat into the atmosphere. This generally is used for areas where there is water scarcity or there are strict water regulations on consumption points. Moving on to the water-cooled system, the fundamental components again remains the same: evaporator and a condenser. What we see here, since it is water-cooled, what it means is that you use water here to cool the condenser, absorb the heat from the condenser, and this water rejects the heat in turn by passing through a cooling tower. So there is a thermodynamic graph for your reference. I will not be teaching thermodynamics now, but I will shortly explain the process in simpler terms. Let's revise fundamentals. You have an evaporator where the refrigerant absorbs the heat from the medium. It could be air or water. The medium gets cooled. You have a condenser where the refrigerant rejects the heat into the medium. Again, the medium could be air or water. And you have a compressor and an expansion wall which enables the refrigerant to do what it is meant to do, that is absorb and reject heat through the process of compression and expansion. This table, you see three terms, that is reciprocating, centrifugal, and screw. These refer to the type of compressors in the equipment. The choice of the systems are dependent on the cooling capacities and application requirements. So if you see, this gives you a comparison where you can once you get the slides, you can have a detailed look into it. So it gives a brief understanding of what are the different types of compression systems available and what are the technical capabilities or the available parameters that are applicable to this individual types. So it gives you the capacities, the specific power consumption values, and approximately what kind of refrigerants are available or is used for the specific type of compressor. I remember one of the previous presentations, one of the participants or the attendees was asking about refrigerant details. So you can have, once you get the presentation, you can go through this hyperlink here where you have a complete list of refrigerants. There are almost 200 types of refrigerant designations available under the categories like, methane, ethane series, or propane, and different organic and inorganic compounds. So you'll have a better understanding on what are the different types of refrigerants available. If one is also interested, okay, the efficient or the most sorted refrigerant will also depend on the system that it is being used for. So not all the refrigerants will be used everywhere. The key takeaways from this table would be to see what are the available capacities for what type of compressor systems that are there in place. Now, this is not limited. You have a lot of information later on which you can have a look. For example, the specific power consumption these days you can come across is as low as 0.47 kilowatt per TR. Also, there are systems there, but this is the most common ones which you come across. Moving on to the vapor absorption systems, the process is slightly complex here, so I will again not get into the details, but I do have slides explaining the process. If someone's interested, I can share them later on. But what we need to note here, what we need to understand from what the vapor absorption system is that this particular system uses heat as a source, as a major energy input. Electricity is required, but on a very minute level compared to the vapor compression systems. And the water here is actually the refrigerant. And there is another component called lithium bromide, which acts as an absorbent to function the functioning of the system. So this table here gives different types of variable absorption machines that are available. Key takeaway from here is that the ability to choose the type of the system based on the heat source you have and the heat quality that you have. So, for example, if any of your building or your industries have as minimum as 85 degrees centigrade hot water that is available and it's simply being into the rejected into the drain. I mean, if it is of significant quantity, then you can actually utilize that heat content, and you can pass it through a VAM machine, that is variable absorption machine, and you can easily get about almost 30 TR equivalent of cooling load capacity chiller in place. So yeah, this table gives you a brief comparison of between the vapor compression machines and vapor absorption machines. Vapor compression machines are the ones which we conventionally use in our day-to-day lives for air conditioning requirements. What we see is obvious that this particular category is more efficient compared to vapor absorption machines. So why do we introduce vapor absorption machines is at the point where you have waste heat that is available, then that is the time where you can use the vapor absorption machine, where you do not have to rely much on consumption of high electricity or electrical energy. And this, I think most of you are already aware of, is evaporative cooling. It's basically air is brought into close contact with the water to cool it to a temperature close to the wet bulb temperature. Mostly this is used on shop floors. This is something where most of the households also use in the name of desert coolers, wherein the water is sprinkled with the help of a pump or a sprinkler on a filter, and you enable air passing over through it, which gets cooled, and you would be enjoying that cool air, right? So one thing you need to remember is that this is generally effective and comfortable to use in only dry and hot climates, not definitely not recommended for already humid climates. Under the heating part, I will be sharing different types of heating systems which are used for HVAC systems. Usually the most common and the applicable ones include solar thermal, boilers, heat pumps. I will not be covering the geothermal source here now. Here you see basically active solar systems, solar heating systems are used, which use the solar energy and transfer that heat into a fluid. This particular fluid, it can be either liquid or air, and generally for storage purposes and all, you generally use liquid, that is water mostly. For heating purposes, again, you can also use boilers for hot water generation or steam generation. They could be gas-based, electrical-based, or oil or diesel-based. This is an integrated system, which is mostly recommended for an efficient use, wherein you use the solar collector, solar thermal, for heating your water, and then so that it enables your boiler to actually consume less energy than it is supposed to consume. Heat pumps also generally operate on the same vapor compression principle, but similar to what we have seen earlier for cooling and air conditioning segment. It is mostly for climates with moderate heating and cooling needs. Heat pumps, offer an energy efficient alternative to furnaces or boilers. Uh, like your refrigerator or other air conditioning cooling systems, heat pumps can use electricity to move heat from cool space to a warm space, making the cool space cooler and warm space warmer. So the difference is with the conventional air conditioning unit is here what you see is heat rejection happens indoors and the heat absorption happens outdoors. So that is, it's basically reversing the concepts here. Further on, most of us would be where heating is required. They also tend to use these electrical resistance based heaters. Most of them are portable also for rooms and all. Moving on to the ventilation part, because since it is HVAC and the V part, the ventilation part, it's also a major component, and you have fans and blowers which are involved here. This particular slide here shows the different types of fans and blowers that may be used for various applications depending on the flows and pressures that one is working with. And this generally the efficiency of the system is also dependent on the suitable installations, that is the type of fans and blowers with respect to the desired applications, as we discussed just now. So you can see here, based on the flow and pressure requirements, what type of equipment that will be required, or what type of fan you want to choose will be, you can have a look here, and then later on you can also compare and see if you already have certain fans and blowers, is that the right fan or blower that you have, by comparing into with this chart here. Moving on to pumps. So this is a detailed classification of different types of pumps available. But for HVAC systems, mostly they use centrifugal pump, which is most commonly used. And for cooling towers, these are the different types of cooling towers that are available. But again, for buildings and HVAC systems, these are the two most commonly used cooling towers. That is the induced draft counterflow and cross flow type. So we would be getting into the technicalities now. I'm sure by now you are aware of energy efficiency labeling and rating and all. We talked about this in our earlier presentations also. So I'll take this opportunity to introduce you all to the content that is either less available, or even if it is available, it is usually scattered around. So this presentation can serve you one place purpose, where you can always get back and revise and review some formulas or important concepts and all. So the scope will be covering for a larger building here, like commercial building, office parks, and hotels and all, for centralized systems where the systems are bigger enough. But this can also be adopted for your smaller systems, that air conditioning or other equipments. So this is basically typically a chiller, and then you have the auxiliaries that are cooling water pumps or chilled water pumps. You have air handling units and cooling towers wherever applicable. Before moving into the technical details, we need to understand that certain units, the TR, tons of refrigeration, which is actually used to measure the cooling effect of the systems. This is the definition what you can read through, and the conversion formulas that are available here. This is an important slide. You would be this represents three different types of energy efficiency ratios. It's not different, I would say, but it's mostly one of these three forms. You find mostly the efficiency ratios being represented in most of your systems. You can mostly find them on your design details or nameplates of the air conditioning or heat pump equipments and all. So if you find one, or if you are able to evaluate one, you can always convert them into another terms based on this conversion formula here. So generally when an auditor or an analyst who comes to measure the performance of your systems, the chiller system, he or she would be coming and trying to first measure these different parameters, like temperatures and flow rates and power consumptions. And then using those parameters, they would be calculating what is the cooling load that is being handled by the chiller, or which also translates to what is the cooling load of your building. So this is how they can evaluate what is the cooling load. And based on that TR that is evaluated, they based on the power consumption that is measured, they come down to evaluation of specific power consumption. That is, this is an example I'm giving you for your reference. So you can use the other conversion formulas that I shared you in previous slides to convert this specific power consumption value into a COP or energy efficiency ratio. This slide gives you some rough conversions or rough estimations of your cooling loads. Just remember that this is just for reference purpose and indicative purpose, and you should not be using this for detailed investment grade activities. But it gives you a rough estimation of how much your cooling load should be, if in case you are planning to buy a new air conditioning system or something like that. This slide gives you a brief introduction of how pump performance testing is done. So basically the auditor or the consultant would be measuring these different parameters for a pump motor system, and then would be using this equation to evaluate what is the efficiency of the system or the pump efficiency. I've also included an example here for your reference later on. If you are able to measure the parameters and evaluate the performances, well and good, but most of us generally do not have the luxury of having those sophisticated instruments to measure these parameters. So sometimes what you can do is you can actually demand your pump supplier for a pump curve. It looks something like this. With the help of this curve, also you can, and with the help of at least one parameter, you can actually deduce the other parameters. So for example, if I have any one of the operating parameters, then I can actually link using the pump curve and estimate what is the other two parameters, or what is the efficiency and all. For fans and blowers performance testing, one important instrument that is used is petard tube. This slide shows how to use a petard tube and what are the different parameters to be measured. So in basically you use this for evaluating the or calculating the measuring the airflows of through the ducts. Generally, this is used for a large air handling unit ducts, and for buildings and malls and some bigger commercial complexes where you have centralized systems in place. So for example, this is a large blower, and this is you have these points of measurements and all. So if someone's really interested, you can get in touch with me, and I can share you the sources where you can find a detailed description of how to measure these values. So yes, basically you would be measuring the velocities, and then you will estimate the flows, uh, and by the end you will be evaluating what is the efficiency of the fan, all based on the parameters that you have measured. You can also similarly, like pump curves, you can also ask your supplier for fan curves if you think this measurements and all are quite complex, and or you do not have the intention to carry out all these detailed measurements. You can always ask for the fan curves from your supplier, and then you can have a look and to estimate roughly what are the different parameters that is being operated at which the fan is or blower is operating at. This is again for the cooling towers. These are the different parameters that are measured. Here you have additional two parameters, that is dry bulb temperature or relative humidity, that is being measured apart from the work consumption and airflow rate and the water temperatures and all. This slide gives you the different reference parameters through which you can evaluate and then see how your cooling tower is performing. So these are something which you can once you calculate, you can actually compare this with your design details, and then see what is the extent of deviation, what is the gap, and then further investigate why this particular gap or deviation is happening. Similarly, for air handling performance air handling unit performances. You measure the different parameters. And for example, I'm showing you how to evaluate the performance of the air handling unit based on the measured parameters. For heat pumps, generally you come across on nameplates or design details, it is usually the performance is given in terms of COP, that is a coefficient of performance. So generally, what it actually means is say if it is measured if it is mentioned as COP of 4, then that means for the heat pump actually releases 4 kilowatt of heat, equivalent heat, and consumes 1 kilowatt of electric power. For boilers, the output mentioned here is generally for the output here on the numerator. It is mentioned here for steam, but you can also calculate for water, hot water. This is this type of calculation where it is nothing but output heat by input heat. It gives you it is more representing a direct method of calculation. There is another indirect method of calculation which is more accurate, but it involves a bit of stoichiometric analysis also. So I would not be getting into the details again of that, but I can always direct you where it can be read and where you can actually use it. So yes, how to save energy? You would be coming across several energy efficiency measures and recommendations all over the internet and all over different books and case studies and all. So I'll try to be quick, most of which you already know. Uh, I mean, something as common as following the best labeling practices or utilizing inverter integrated products for air conditioning and refrigeration systems, uh, utilization of capacity control, taking advantage of capacity control technologies to optimize your energy consumption based on your demand variations. So this is one of the case study from a building here. I'll directly jump into the result. If you see this line here represents the for results for specific power consumption for chiller 1, which was connected or integrated with a variable frequency drive, and this one here is represents specific power consumption for chiller 2, which does not have a variable frequency drive. It is, you should note that both the chillers are of same capacities and were subjected to same conditions. Uh, and so it gives you a picture that on having a variable frequency drive for variable loads, this system with the VFD would actually be more dynamic enough to respond to the type of loads that are being demanded, and it can optimize its energy consumption accordingly. So this was about, the difference is about on an annual basis 2.2 lakh kWh is the difference between the one with VFD was consuming almost an equivalent of 2.2 lakh kWh less compared to that of the one without VFD. Further recommendations or measures here, basically having variable air volume or air curtains technologies adoptions, and something like we've also seen in one of our earlier sessions about talking about the insulation levels and having a proper envelope coating and window efficient windows with respect to suitable coatings. And again, yes, this is one of the most important ones here. Reducing heat loads in conditioned spaces. Often, what we see, I've seen most of the corporate offices, and wherein you have, let's say, a refrigerator, a coffee machine, and all these things. Everything comes into one conditioned space where the employees can have coffee and have something cool and all. So. If it's possible, these are all, at the end of the day, these are all heat loads. So why do you want to cool these coffee machines and refrigerators also by placing them in a conditioned space? So if it's possible, you can always try to shift these kind of equipments outside your conditioned space so that your actual overall heat load comes down. This table gives you a brief introduction about what are the different capacity controls that are used for different types of vapor compression systems. And this is another important table which you can, I would recommend you to note down the numbers also if possible. So it gives you thumb rules where you can actually apply for your day-to-day quick assessments wherever applicable. For example, you might have come across many recommendations or suggestions wherein they ask you to increase your set temperatures or in your of your air conditioner by like say 1 degrees or 2 degrees, not to maintain at low 18 or 20 degrees, but you can slightly go up to 21 degrees and all, right? So the reason is something like this. You can have a look here. For every 1 degree rise in your set temperature or nothing but the evaporator set temperature, you would be able to reduce your energy consumption by 3%. So that is the reason why, every time, if it's possible, if you think you are comfortable at maintaining a 23 or 24 degrees centigrade set temperature also, please do it, because equivalent percentage of power consumption would be saved. This again is one of the case studies for in one large commercial complex, wherein this is more not just limited to one specific measure, but there were a lot of optimization that was done, mostly with respect to the chilled water flow rates and the pressure variation, pressure optimization for the cooling water side, and the airflow optimization was done. So all these type of measures were implemented, and then you can see before what was the power consumption, and after implementation what is the power consumption. So it is important, it's not, you should ensure that an holistic and overall approach is maintained to save energy, because you should ensure that targeting one specific area or one specific auxiliary component uh, to save energy is fine, but it should not have a negative impact on the other components, because as I mentioned in the initial slides, you have to look this as a whole system, not an individual component. This is we come across most commonly in, again, office spaces where you have large spread halls, and there are a lot of people sitting and working in that one big hall, and the entire hall is being is air conditioned. Most of the times it so happens not everyone is present in the hall or in the room, and but the entire hall is being air conditioned, is being cooled. So this is simple wastage of energy, right? So what would be recommended is try to have zones for your air conditioning equipment, wherein depending on a specific zone, if that particular zone detects that there is no people there, or the temperature set points have already attained, then the systems like VRV systems, or variable refrigerant volume systems and all, they can actually regulate the extent of refrigerant that is flowing into that particular zone. So that in that way you have less work on the compressor done here, and less energy consumed. Further, talking about energy efficiency measures for fans, blowers, and all, pumps. So one of the most common thing is oversizing. People generally do install oversized equipments. It's quite a common task where I've seen mostly for airports generally. Now they plan, airports generally trying to plan for next 10 years or 15 years down the line, what would the footfall be, or what is the number of passengers they would be handling. Based on that, they would be designing the systems and keeping it in place. But what happens is, lately we see that every 3 years, every 5 years, there is a new technology coming up. So it is always recommended to have the best technology that is available now for the right design optimal values for the current load conditions, so that because the conditions would vary after a certain number of years. That time you can always upgrade your systems with that with the requirements based on parameters required for the conditions in 5 years or 10 years down the line. That you can look into that system later on. So what, based on you should make sure that you cater to the needs that is actually required for this moment, or at least 1 to 2 years. That's fine, that's good. Because if you go ahead and start integrating large capacities for a smaller requirements, capacity requirements, then you would be operating your systems in part load conditions. There would be a lot of inefficiency coming up. So yes, you need to ensure that you avoid that. For fans and blowers, these are the two types of most commonly used capacity control mechanisms. One is you have a damper, and then you have inlet guide vanes. Apart from this, you also can use variable frequency drives for fans also. But that's slightly on an investment cost wise, the VFDs tend to be a bit more expensive. So this is the next best efficient option where you can use. So this is where the larger volumes are not required, where generally when you do not have large volume requirements of airflows, then you can use this. Basically, it reduces there is relatively less pressure reduction compared to that of the damper, where here you have a lot of energy loss because of the pressure reduction that happens. This table here gives you a brief information about the different the efficiency ranges for different types of fans. So you can also use this table as a reference to choose the efficient fan that is or the blower that is available for your. Of course, you need to ensure that it also serves your purpose of usage also. Sometimes you do not have to really go for heavy investments in order to save energy. It could be something as simple as these, because these kind of measures are something which are overlooked. This is one of the example for a commercial shopping mall building actually. So where they need to pump in a lot of fresh air into the public space, right? So you have two fans here, fan number 1 and 2. So the ideal case is one fan operates and the other one is on standby. Now, what we have observed is the number one was operating, number 2 is on standby, but part of air that is being blown into the user side, part of air actually returns back to from a common duct or a joint to the through fan 2. That is, it's nothing but wastage of energy. So what was a simple step that needs to be done is to simply close the common damper that separates the ducts between, that separates the path of these two ducts, right? So that if that is closed, then the problem would be solved, and it was immediately closed after rectifying it. I mean, after mentioning it. And yeah, it is not much, but yes, there is a significant amount of energy reduction that takes place. Furthermore, you can go into technology upgradation also, wherein this is for an example, we were talking about variable frequency drives for fans and all. So lately you have better technologies coming up, that is EC motors or electronically commutated motors. On comparison, if you see, you have a variable frequency drive, you have a motor, you have a blower, but in this technology, everything is compact, concise within one small space. This is quite efficient, and it's less in terms of noise emission also. So this is the data based on the field results that we have measured. So if you see, before the technology implementation, after the new technology implementation, the power consumption has drastically reduced, maintaining the same flows. So almost 36% to even at a time 60% of the energy savings were achieved. So for heating, it's again common measures, trying to have insulated pipelines, have balancing walls, have metering in place and monitoring in place. One thing I would like to stress here is that yes, most of us use electrical resistance type heating, and some of them would also have idea that a thought that electrical resistance are 100% energy efficient because whatever electricity it consumes, it dissipates into heat and into the space, which is true. But if you look into an overall aspect here, where is that electricity coming from? It's coming from a power plant situated somewhere far away from your usage point, right? So, and if you actually consider the overall efficiencies, then there's already a 30%, close to 30% energy loss that happens by the time the electricity travels all the way from the power plant to your plug point. So yeah, you need to, if you're really efficiency conscious, if you're really calling yourself green and trying to be more sustainable, then you would also give a thought on that regard. So these are the different measures for the boilers, wherein I mean, generally it is not a complicated process for a small baby boilers, but for larger boilers, then yes, these systems can get a bit complicated. This table gives you differences between what a low efficiency boiler is, a mid efficiency and high efficiency boilers are. You can see the efficiencies can be as high as 98%. And one last case study for the heat pumps, wherein, as I was mentioning earlier also, these heat pumps can also be used for as an alternative for the boilers if the climatic conditions are suitable. And one of the places where this was implemented, they were directly an annual savings of diesel savings of about 13.5 KL of diesel savings. So yes, I'm sorry again. It's a big subject. I wished I had a lot of time and to explain more case studies first. But yes, if you can get back to us, we can direct you to relevant sources on the website, which helps you understand much better on the topic. Thank you.
Thank you very much, Rahul, for your very thorough presentation. Now, the next speaker is Clara, but before we go to Clara, I've been asked to conduct a few questions for the audience in order to make some conclusions. So, the first question that we would like to ask you is, what does an energy efficient lighting mean for you? And the options you have: using less energy for lighting, using LED bulbs, improving the lighting control system, all of the above, other. So I'll give you a few seconds just to respond. So thank you for the responses. Let's see the results. And the results are 31% chose using less energy for lighting, 2% improving the lighting control system, and 67% of the above. And the other question that we would like to conduct is, would you consider the lighting systems in your municipality to be energy efficient? And you have three options: yes, no, I don't know. As always, we'll give you a few seconds to respond, for you to respond. Okay, let's see the results for this question. And the result is 30% responded yes, 55% responded no, and 16% responded I don't know. Thank you very much for your responses. And now I'll give the floor to Clara, so in order for her to start her presentation. So Clara, the floor is yours.
Thank you very much, Aris, and welcome everybody to this session 3.5. After this very interesting and thorough presentation from my colleague Rahul, let me take you through this session on energy efficient lighting systems. Now, the objective of this session is to share insights on key aspects of energy efficient lighting systems, as well as potential actions and tools to improve the energy efficiency of lighting systems. Given the audience today, I will highlight the information that is most relevant in the context of energy efficiency and municipalities, and the session will take around 20 minutes. It is divided in two main blocks: a more theoretical block covering fundamentals of energy efficient lighting systems. This will take around 10 minutes, and a more practical block in which I will go through the key steps in implementing energy efficient lighting systems in your municipality, revising those aspects or those points in which the C2E2 can offer you support, mostly in the form on 2 energy efficient lighting tools, one on an energy efficiency assessment and the other one more focused on the financing aspect of it. This will take around 10 minutes. So in total, as I mentioned, 20 minutes. And in case you have any questions or comments on the content I'll be sharing, you'll have the opportunity, to raise them in the Q&A session scheduled at the end of the session today. So starting with some fundamentals of energy efficiency lighting systems, I see that based on the poll results, I understand that many of you already are very well aware of much of the information I will be sharing. But let's have a quick overview at basic ideas and concepts to make sure that we're all on the same page. For this, as I always tend to do, let's start by addressing the question why. Why do we need to take action in lighting? Why is it important? Well, lighting accounts for approximately 20% of the global electric energy consumption. That is around 2,900 terawatt hours, so nearly 3,000. Furthermore, projections by the International Energy Agency show that if governments only rely on current policy, global electricity use for lighting will grow to around 4,250 terawatt hour by 2030. That is an increase of more than 40% as compared to the current electric demand. And this increase is mostly due to the world's growing population and increasing demand of electrically driven devices and services, mostly in emerging countries. All of this shows that lighting is indeed of great importance when reaching out to carbon reduction targets and avoiding the 2-degree temperature increase, and of course the dramatic consequences that it would have in our habitat. But the next question again is why, again a why question, why should we focus on energy efficiency? Why should we implement energy efficiency measures in our lighting systems? And what is the energy and respective CO2 emission saving potential that we can expect from these interventions? Well, as you can see in this figure from the baseline emissions, energy efficiency measures in lighting can derive in 5% of carbon reduction, plus more than 5% from the 25% from buildings. That is around 10% of global emissions. Now, as much as these percentages can vary, of course, based on the specific country, region, and context, it is a very clear indication on why energy efficient lighting systems should be tackled. Another very relevant fact, now looking at municipalities, is that street lighting plays an essential role both for security and for quality of urban areas. But worldwide, around 90 million lighting poles alone account for more than 50% of the public energy consumption and about 60% of the public account costs. The good news is that energy efficient lighting is one of the most cost-effective ways to reduce energy demand and respective CO2 emission. Innovations in lighting, such as LED, as we will see later on, promise an energy saving by sometimes even more than half. And a notable reduction of the maintenance costs associated with it. So energy and efficient lighting is both an urgent need when looking at from an environmental point of view, as well as a great opportunity when looking at it from a purely economic perspective. Now, before we move forward, let's look at what exactly do we mean with energy efficient lighting systems. Well, we refer to a way of, in overall as a definition, a way of maximizing energy use while minimizing individual carbon footprint for the arrangement or effect of lighting in a specific context. In the case of this presentation, as I mentioned earlier, we'll be focusing mostly on municipalities. This can be divided into 2 main areas: lighting in buildings and street lighting. Lighting in buildings refers to all the lighting systems you can find in a building, as I briefly explained on the previous presentation I made on buildings. Now, this graph to your left shows you an overview of what are the percentages of the total energy consumption for lighting per building typology. And as you can see, for lighting purposes, building uses that are most likely to be municipally owned or managed, such as schools, offices, administrations, etc., account for the biggest share of total energy consumption. Now, looking at the second aspect of energy efficiency, lighting systems, that is the one related to energy efficient street lighting. This is defined as the public lighting for public spaces, including traffic light signaling, and the objective is fourfold and even more probably, but let's highlight the four main objectives. First, to make the traffic and obstructions on the road clearly visible and avoid any kind of traffic accidents. Second, to make sure that the streets are more attractive. Third, to increase the community value on the street. And last but not least, promote safety and reduce criminality. The main components are street lights, luminaires, traffic lights, and ideally also control mechanisms. Now, in this presentation, I will be mostly focusing on the latter one, the street lighting. But it is important to note that many of the principles I will be sharing can also be applied to lighting in buildings. Delving into street lighting then. Now, what makes an energy efficient street lighting system? What makes it efficient? How can we recognize an energy efficient lights versus a non-energy efficient lighting? Well, in this case, we're focusing it in a LED system versus a non-LED system. And what are the technical differences between one and the other? There are many types of bulbs that are non-energy efficient used in public spaces. And unfortunately, the most common type of luminary for street lightings around the world at this moment today. These are mercury vapor and sodium vapor, metal halide, incandescent, compact fluorescent lamps, and fluorescent tubes. Non-energy efficient lightings typically don't have any control or smart systems. It's simply connected to the electricity grid. As for the energy efficient lighting systems, it is composed of two main aspects: LED luminaires, as we mentioned earlier, and lighting smart control systems. LED stands for light emitting diode, and it is an electrical light that produces light using a light emitting diode, as the own definition or own name specifies. And a control system is a smart network of lighting control, which allows you to control the lights in a particular space based on the specific needs and uses. Having a closer look at the energy efficient street lighting systems, this can be, as I mentioned, broadly classified into these two main aspects: LED bulbs in the luminaires and lighting control systems. But let's have a clear overview of what do we mean? What would be the energy efficiency measures related to each of them? In terms of LED luminaires, it would mean implementing LED lamps in the cases of new street lights or luminaires in general, but also the replacement of non-energy efficient lamps in outdoor lighting for LEDs in the case of already existing poles. When it comes to control systems, some of the actions that can be undertaken are related to light zoning, which is the selection of spaces or areas that should be illuminated, lighting control mechanisms, which can also refer to the installation of presence detectors in areas of sporadic use, like in the image you see to your right or the right of the slide, where the luminaires detect when the traffic, be it a pedestrian or a dynamic motion such as a car or a bicycle, and it activates, leaving a distance range to accompany the movement of this agent. Now, lighting control can also entail adjusting the use of to light hours to capitalize on daylight, as I mentioned or described for the buildings session. For instance, from winter to summer, the use of these luminaires can be adjusted to optimize on all the daylight you have. All of these controls can be centralized or programmed, monitored, and verified, not only in terms of energy use, but also in terms of cost, through lighting management systems, as we will see later on in this presentation. The table in this slide shows a comparison of the various technical specifications between LED and non-energy efficient lighting systems that we have seen before. I will not go through each of them, but I want you, however, to highlight that the technical performance of a luminaire is typically assessed by its efficacy, which is based on the wattage and the lumens, where you simply divide the number of lumens by the number of watts, and that gives you the light energy efficiency, so to speak. Also the size of the bulb, depending on the use and the space you want to eliminate, its lifetime, which impacts the costs of the new bulb, but also the time spent on planning and executing its replacement, not to mention the potential risks and hazards of not having light during that time in that space, in that public space in this case, but also correlated color temperature, which is a measure of light source of color appearance. Another indicator can be the color rendering index, which is a rating index commonly used to represent how well a light source renders the colors of objects that it illuminates. And another indicator is the durability, how long the luminaire will last, which is related, of course, to the lifetime, but also related to any shock or any incidents that will happen to the bulb. How will it react? And in terms of cost, it does indicate this could be the initial cost, but most importantly, it has to do with the lifetime of the bulb, as I mentioned earlier. So it's not only about how much it will cost once you buy it, but how much it will cost during its use. And that is something that needs to be taken into consideration when assessing the, let's say, viability or the appearance of this solution. As you can see, there are many other indicators, and as I said, I won't delve into each one of them. I just wanted to show that all of these indicators are aspects of LED scores. LED scores much better than the rest, sometimes by factor 5. So the key ideas I would like to share with you and to remember is not the facts in the table before, but really the following. The advantages of the LED lightings are it is the highest efficacy light, the indicator of energy efficiency, as you might recall, having the lowest running cost, and in terms of operating lifetime, it's typically more than 20,000 hours long. It offers a good optical control and excellent control rendering without containing any mercury. In this way, LED bulbs use less than 70 to 90% energy as compared to incandescent mercury vapor or CFL luminaries, and up to 40 to 50% with respect to the metal halides, sodium vapor, or halogens. Control and dimming actions can add up to 30% additional energy saving to this. And LEDs last longer than a regular bulb, actually more than triple, if we take into consideration, as I mentioned, the complete lifetime. All of this leads to a total of 40 up to 60% of annual energy demand reduction and subsequent CO2 emission reductions, not to forget the savings on public's budget, which in turn can help to recover costs in a very short period of time, and even more, allocate the saved budget into other relevant public services instead. Now, looking a bit more in depth into the lighting control systems, the main control strategies are very basic. First, daylight harvesting, making sure you make the best use of the natural light, as we mentioned earlier. Dimming, which is basically reducing the intensity of the light to adjust it to the real-time needs. And optimization use, so adjust all of the features to reduce its energy use during its use, to the minimum. And there are various ways or degrees in which it can be controlled. Through autonomous control, in the case in which each luminaire will have its own control system, a centralized control where all of the information will be channeled to a central agent or program, and a dynamic control where the daily or even hourly data is used to adapt and adjust the lighting systems to better optimize its use for the time lapse it's defined. Now, to make sure that the light activates only when it's needed, we need sensors. The types of sensors can be classified into motion sensors, as it's the case of the image of these lights, as explained earlier. These detect when somebody, such as a pedestrian, or something such as a bike or a car, is entering or leaving the space, and they will activate or deactivate the light accordingly, and also create a path accompanying this agent. You also have time controllers. They switch the lights on or off automatically according to the schedule set manually on the system, but can be adjusted whenever necessary. And finally, you have light sensors. These measure the brightness of the daylight and then calculate how much artificial light to provide and support to it. And of course, the brighter the daylight, the lower the amount of artificial light it will provide. It is important to note that the sensors can be, of course, combined depending on the different needs and uses. Now, all of these various aspects that I just described can be designed, programmed, and monitored using lighting management systems, which can lead to substantial energy demand reduction and overall cost in the energy efficient lighting, as I explained before. A lighting management system provides information about the luminaire status for proactive maintenance and early detection of failures. It can also support individual adjustment of the illumination through smooth dimming. They offer the possibility to read and set the luminaire operating mode, as well as the power consumption and operating times. And it typically offers real-time profiles with day-dependent dimming levels, as well as an active monitoring of the luminaire temperature that can be adjusted, again, according to need. But these are just some of the features. You can find different ones according to the different profiles of the cities or the different management systems per se. They're composed of very few simple elements. First, a power line communication, then a concentrator to collect all of the information for the different power lines from the different luminaires, a hardware connecting the luminaire to the control system, normally wireless, and a GPRS wireless network, which receives the signal and then sends it to the monitoring center, which has the software as an interface and control panel for the data. Its great advantage is that it allows real-time and accurate data. It can automate any process or any progress. It allows to adjust the lighting system based on real data. It can even be programmed to support the city or municipality in facilitating critical municipal services such as emergency responders, parking, traffic flow, or even air quality monitoring. And this might seem like a very fancy and complicated system, but these programs are typically less complicated than any app we would have in our smartphones. They're built to be user-friendly and intuitive. Furthermore, the investment cost for lighting management systems are typically recovered in a few years after its implementation through the energy savings. In this way, it offers the potential of a connected, intelligent lighting as an additional energy efficient and smart city tool. Now, before we move on to the next block, let's revise some of the benefits for municipalities of energy efficient lighting systems that we have seen already. These can be clustered into four main aspects. First, lighting quality. LED street lighting offers a significant improvement over non-energy efficient solutions. The white light of the LED system offers better color renditions and object detection, which enhances safety and comfort. LED street lighting also offers better optical design opportunities, which cannot be achieved with conventional sources, resulting in better illumination and reduction of light pollution. Second is energy efficient or energy saving, LED street lighting is more energy efficient than conventional technologies, with a design that saves an average between 4 up to 80% of the energy, depending on the technology being replaced. Next would be related to the requirement of maintenance, so less maintenance required. LED street lighting provides a significant longer operating life than conventional technologies, as I explained before. So there's a few lamp changes and less downtime, along with the expense and public risk associated with the street light blockouts or any kind of non-lighting space. And last but not least, when coupling intelligent networks with LED street lighting systems, such as lighting management systems that we just saw, the benefits increase as they can support municipalities in managing and facilitating other critical municipal services, such as emergency responders or air pollution, as we mentioned earlier. In a nutshell, energy efficient lighting enables to cut off costs while improving safety and service. And in the case of municipalities, it is an opportunity to lead by example. Such actions can even improve the image of municipalities by promoting awareness on the environment and energy efficient development of the city or municipality, as well as helping to acquire experience in such projects and test if the necessary framework conditions to undertake such actions are indeed in place. Okay, but now let's bring this theory to a bit more practice. Let me share with you a few examples of municipalities around the world that have already implemented energy efficient lighting, to then link it to you and to the steps that you can take in order to implement energy efficient lightings in your municipality. And I know some of you have already street lighting in place, but it was not the majority of you according to the polls. So let me also highlight some of the steps in which the C2E2 can help you in this process, including the tools that we have developed for this. Let's revise some of the, I'm sorry, I went backwards. Yeah. The first case I would like to share with you is the case of Buenos Aires in Argentina. The city of Buenos Aires has set itself the objective to replace all inefficient luminaires with state-of-the-art energy efficient ones. The project started in 2013 and was finalized end of last year, so end of 2020. And as of now, it has achieved energy savings of 50% of its total energy bill. That is around 85,000 kilowatt hour per year, which is equivalent to the consumption of 25,000 homes. It has also achieved a reduction of 44,000 tons of CO2 emissions per year, and it is estimated that it will have triple the lifetime of a conventional lighting or luminaire. It also offers better facial recognition based off the white light they radiate, which is very important for security cameras, for instance, as well as less luminic pollution. It is conceived through a centralized management system, as I explained before, which includes a 40% reduction in repair time and reduction of 30% of maintenance cost. With this project, Buenos Aires is not only saving energy and budget, but it has also become the first Latin American city with 100% LED luminaires in its street lighting. Another example I wanted to share with you is the case of Cascais municipality in Portugal. In 2005, energy consumption from the public lighting represented around 80% of the total energy consumed by the local government for public infrastructure. And they plan to replace more than 307 luminaires with an overall investment of 160k euros, which they intend to recover within 3 years. And this will lead to a reduction of 88% of kilowatt hours per year in terms of energy consumption, and 200 or nearly 300,000 kilograms of CO2 emissions per year. And these are just 2 out of many municipalities around the world that are implementing energy efficient lighting systems. More and more municipalities and cities are taking action in relation to this, as it is a very cost-effective, low-hanging fruit to lower the energy demand and cost of the municipality. But let's link this to you now. What are the key steps to implement an energy efficient lighting system in your municipality? Where to start and how can we help you? Well, there are 5 main steps that you can follow. The first one is to put together the necessary team of experts that have the know-how to make this happen and are committed to working on reducing the municipal energy cost. This team should hold a diverse range of skills and experience, but they should somehow have the know-how of the different energy efficient aspects of the system. The second step is to develop a rapid assessment or a preliminary assessment. This is a relatively quick preliminary study to collect key information prior to designing the intervention. It should contain key environmental, technical, and economic aspects on the potential of the energy efficient lighting improvements, so you can have a preliminary basic understanding of its potential. To this end, we have developed the street lighting tool, an energy efficient calculator in the C2E2 that I will explain in my next slide, and hopefully can help you in this step. The next step in the process is to define the project. Based on your rapid assessment, you will need to define whether the exact interventions needed, who are the people involved, and what is the timing for this. The next step is to secure the budget. For that, it is important that you first know how much budget will be required to execute these actions, where is the financing, where can you find this financing, and how to attain it. This can, of course, be done through project bundling, as we describe in this training. And to this end, again, we have developed a tool in the C2E2 to help you navigate and know what are the best financing streams you can get hold of in order to implement such actions. And last but not least, execute or implement the project. Now, that means undertaking the necessary works in terms of energy efficiency lighting. And again, bear in mind that this can not only refer to the energy efficiency lighting, but that can be bundled with other actions or other energy efficiency improvements in your municipality. And it will require measurement, reporting, and verification schemes, so MRV, as my colleagues will describe later on in the later sessions. Now let's have a quick look at the street lighting energy efficiency calculator tool that has been developed by the C2E2 and the Energy for All initiative. The goal of this tool is to assess the potential savings from the switch to LED lighting from the street lighting system in your municipality. The data required in terms of general aspects are the name of the municipality, the country, the annual light hours, the electricity price, and the emission intensity. In terms of the lighting inventory, it will ask you about the current lamps in your municipality, the types, the power, the stock, that is the quantity of them, and the price per lamp. Not much more than that. As an output, you will have the savings compared to the current system. So the electricity consumption, the financial total investment required, but also the return on investment, and the CO2 emission savings. The results are presented both with and without lighting intensity control systems. And please note that this tool is free for everybody to use and user-friendly. It's very quick and easy to navigate through it. It's actually fun to do it. And you can click in this link, the one I share here above. Let me see if I have the mouse here, but no, I don't. But basically, where it says click here to access the tool, and you will have direct access to this tool. Now, having a look at the street lighting financing tool, the goal of this tool is to guide you into which are the optimal financing mechanisms or instruments to implement the energy efficiency lighting systems in your municipality based on the project and, of course, your municipality and country conditions. It is an Excel-based tool, the same as the prior one, actually. And if you click again in the link I share here above the image, it will redirect you to the website where you will download this Excel file, and you simply have to answer yes or no questions. As I said, very easy, and at the end of it, it will offer you a report that you will then have access to the best financial scheme that can be used. This takes around 10 to 20 minutes to complete, not more than 20 minutes for sure. And you will learn actually through the process. So it's not only free, user-friendly, quick, but it's also actually fun and educational to go through it. So I would really encourage you to try it out. And if you would have any questions or issues, you can contact us at any time through the email we show or we offer in the website. And yes, with this overview of the tools, I will wrap up this session. I hope this information was useful for most of you at least. Any questions or comments, do not hesitate to contact me or visit our website. And yes, I'm looking forward to the Q&A session at the end of this module. Thank you once again. And the floor is yours, Rahul.
Thank you, Clara. Hello again. I will be covering the session on opportunities for energy efficiency in water supply now. So we would start with a brief look into the status of the water sector, and then we will be looking into the potential energy efficiency opportunities in the system. We will talk about water saving and water energy nexus. In the end, I'll try to introduce you to a water tool that we are developing now at C2E2. So a thorough understanding of the supply system actually gives you a better picture on various challenges that the city or municipality is facing, or they may have to face in near future, provided necessary corrective actions are not taken, right? So it is important that you need to understand your system properly. Water generally, the availability is the main driver for the sustainable development. Now, why the water sector is important? One, it caters to your day-to-day needs, domestic, commercial consumption, industrial requirements, agricultural requirements. It is estimated that the water demand is projected to rise by almost 50% by 2050 compared to the 2000 levels. Number two, it has a direct impact on individuals or an entity's energy consumption. Our present discussion is more on the water energy nexus, that is, the interdependencies between the water and the energy sectors, which are very strong and need to be addressed as a whole to be able to tackle stress on resources caused by climate change. The energy consumption for the water sector usually represents about 3 to 4% of the world's consumption. Higher electricity demand can, we are aware of that it can lead to unsustainable costs of operation for the water supply systems, which again directly affects the public finance, budgets, and tariffs for the final consumers. So generally, the numbers and the percentages that are given may vary for individual countries, regions, or municipalities. For example, for Japan, where the systems are gravity fed, the water energy consumption is about as low as 1% of the total energy consumption. For Spain, it is relatively higher at 5%. In California, where generally the water, wherever the water acute crisis is there, the water is being pumped for longer distances, it is as high as 20%. Now, I was actually assessing some quick numbers for the ECRI region countries also. So the consumption patterns were found to be around with an increasing range, year-on-year increasing range of about 4.4 to 11%. This is only for domestic consumption alone that I have calculated. Relatively high, this is something relatively higher compared to the global levels, the increment on an year-on-year basis. Now with this, we need to understand that a lot of awareness has to be created about water being used as a resource, and about how we value the fact that one has access to water, because not many in the world are actually, even today, have the luxury of having water delivered through pipelines to the taps in their houses. So the way we consume water defines how much water is available and for deprived people also. So yes, which brings me to the third point here: regulation. This is to ensure that there is a win-win situation to the extent possible at all levels. That is energy and water, economics, and of course GHG emissions. Uh, it also involves us to how we promote and educate the efficiencies in practices, production, products, equipment. The pie chart here on the left actually shows you the energy consumption at different stages in a water cycle, and it is clearly seen that about 50 to 60% of the total consumption belongs to the supply component, that is, the extraction, purification, and transportation. Now, we understand, and it is quite evident that energy happens to be one of the significant components of the water utilities overall costs. So tackling this component can actually lead to better budgeting and finance, which again trickles down to optimal tariffs for the customers, and also have a positive impact in reaching larger outreach with respect to water connections, better accountability. We will see some energy efficiency opportunities, explore some points on how we may have to prefer a holistic approach over the individual areas. So first we talk about energy intensity. It is often used to understand and compare the changes in energy efficiency in these water systems. Now, energy intensity is also referred as specific energy consumption, which is the energy consumed to supply a cubic meter of water. You may actually define this metrics as a baseline for comparison with the changed or updated scenario or conditions. Let's say after some improvements in the systems or after some increased demand, or to understand if the existing system is already good or no. This can actually be used further to subsequently evaluate financial savings or GHG emission reductions. Now, one caution one may need to observe here is that this actually is an indicator and it may be required to normalize, which I'll be discussing about in the subsequent slides. The picture on the right here actually shows the various stages through which the energy losses are observed. Where the various energy losses are observed, the energy and this energy water systems are interlinked. For an effective assessment and useful outcome, generally the energy efficiency and water efficiency should be studied together. In simple terms, you observe water losses, then you would obviously be observing equivalent energy losses. Likewise, for example, if you reduce your water losses optimally or optimize your use of water, you will be observing some reduction in your energy consumption also, and this will also be further leading to your reduction in energy costs. So if you categorize different components like shown here, the inefficiencies are easy to spot. So you, in your entire water supply system, you have these all components. It could be transformers, power factors, variable frequency drives, motors, and pumps. So if you actually categorize individually, you can see, for example, you have transformers here. Let's say my existing or old system is 85% efficient, and I know that there is a 96% efficient system already available in the market today. Then yeah, there is enough potential of improvement in terms of efficiency there. Then power factor. I would not directly get into the details of energy savings, but for power factor, but it mostly impacts on your energy quality also. For most of the entities or water utilities, generally they are built on kVAH basis, or they might be having some limited contract demands, or having high penalties if they exceed their maximum demands. So they may have to focus on this power factor point also. For representative purpose, I've given 0.9 here, but I think you will also find places maintaining 0.98 also as a power factor. So yes, of course. I mean, optimal power factor maintenance will actually help you have a better energy quality, low line losses. It can also help you in reduced voltage drops. Importantly, increase the available power. That is, if you have, I mean, it will enable you to have more room for loads in the same fixed grid. Variable frequency drives, generally, the power consumption regulation is based on the user and demand. Now, municipal supplies, they generally might see high demand during the mornings, where everyone in the households are getting ready, go into offices, and also there's a lot of water consumption might be demand might be there. So during this time, the motor pump systems and the utilities would be running at full loads. But during the other time of the days, somewhere in the afternoons or in the evenings where the demand is not much, the pumps or the motor systems would be forced to run on part loads, on inefficiently. So this is the point where during the times of dynamic variations, VFDs can come into picture, help in optimizing the power consumption suitable for the demand. Electric motors, I think everyone is aware of with all the different IE standards and the efficiencies that are available in the market. You can always have a look into the nameplate and see what is the next best efficiency that is available. Further, you can actually evaluate if it is really economical to go for an efficient one or no, and then take a call. Similarly, for the pump systems, I mean, depending on the desired flow head combinations, you can actually define what kind of a pump you need and what are the design rated details it is required. So yes, the initial investments may be high, but if you compare with the yearly losses, and of course adding to this regular maintenance costs, it would eventually justify that the need for investment on energy efficiency efficient systems would be inevitable. So this is again from one of the field studies. I think this is one of the field studies which I took a photo of. But yeah, so if you look into this, it's not just technology-wise or efficiency-wise. I mean, you at times you might have to open the systems if it is a very old system and all. You might have to look into the interiors also at times. So if you see here, you see some corroded or almost damaged impellers of the pumps. So the metal is literally eaten away. So this causes disturbances. This induces inefficiencies that could creep up into the system in many ways, and end up eventually consuming a lot of energy. So usually the best benchmark indices will be design efficiencies in comparison with the operating efficiencies. For example, if your operating efficiency is lower than your design efficiency, then it would be recommended for you to investigate the reasons why this is happening. Is it due to some system mismatch, or is it due to the degradation of the system? Is it due to the some variations in the demand supply gap or wrong design? At times, you may also have to look into the fact that is your design efficiency lower than the available best market efficiency values. So yes, these are something which you need to compare. But sometimes what happens is you do not have the design in place because you might be talking about some very old systems, or or at sometimes you want to actually do a quick analysis or quick comparison between to find out where your system lies. Then this kind of this specific energy consumption values what we derive here using this formula is a better approach for immediate or rapid assessments. So I was actually mentioning about earlier mentioning about the normalization part. So if you see for international standard comparisons, use this indicator, the specific energy consumption indicator. You will be normalizing it to your local values to 100-meter head. So this particular metrics can be used for rapid assessments. For investment grade proposals, again, you will be required to do a full-fledged energy audit to proper, to have measurements of proper flow, head, power, and monitoring to different demand and timelines. So you see here, this is mostly like a traffic signal category or criteria, wherein for an international standards, this is what these values are. So if after calculating your power consumption to your water consumption ratio, specific energy consumption, if your value comes somewhere between 0.27 to 0.4, that translates to an equivalent of 68% onwards efficiency, which is supposed to be in a better region. If it is somewhere in between, then it is moderately operating, and if it is less than 0.54, then it is poorly performing. I'm sorry, this is 0.5 here. So efficiency is one thing, but one has to also decide if the investment for the efficiency is really a good investment or no. So this is where the payback period is evaluated. Even though you have some, even though if you have the same system, same components, same technology, but sometimes you find that payback periods would be varying because the costs or the capex that is involved may vary at two different places. It could be variation in the technology available in the local market, or I mean, in terms of labor cost, transportation costs. Do you have to import it, or is it available locally? So all these factors play an important role there. So ideally, most preferred payback period is less than 3 years. That is, I start getting my returns for the investment that I have made on the energy efficiency activities for is less than 3 years. I mean, something which most of the private players would be interested in. But for large public projects and some governments are fine with 4 to 5 year payback period also. Again, the payback period is also looked into by the banks and financial institutions when you actually look in when you go for seeking loans for or funds for your investments. So this is a case study wherein the National Utility of Guyana, along with American Development Bank, actually studied nationwide water utilities, and then they were able to identify a lot of potential because there was huge water losses that were happening, and they were losing a lot of I mean, they were incurring a lot of utility costs. So they have conducted energy audits and found quite a good number of energy efficiency savings with respect to the improvement potential of in power factors, the improvement of efficiencies in water and motor pump systems. So I mean, the average efficiencies were about 46%, which was quite low. So what the solutions that were recommended later on was, to actually have new water tariffs which actually reflect the real cost of the water, and then they were able to replace inefficient pump motor systems to efficient ones and have a good number of savings. Almost 29% of the efficiency have been improved. So until now we were talking about energy and energy efficiency component of the systems. However, we discussed that in the initial slides, saving water is not the only criteria. Saving water is also another criteria. It's not just energy, because water efficiency also matters. And 2/3 of the energy savings is generally achieved by saving water in most cases. So in order to save water, you need to understand these different terminologies. Something like non-revenue water is something what we define it as the water that is produced but not billed. I mean, this is something like water that is actually supplied to social areas, firefighting requirements, public space maintenance. So basically, you know that this is the amount of water that is being consumed for a specific purpose, but you don't charge them. So this is something you need to be aware of. What is the non-revenue water? Then you should be aware of what is the physical losses. Physical losses are usually the leakages which are happening during the transportation. Most of the, I mean, sometimes if the pipelines are laid underground, the losses would be invisible. But then how you can identify the losses is by having a proper metering system wherein you know how much water is being supplied from the utility, how much is being consumed at the user end. The difference gives you the losses in terms of physical losses or commercial losses. Commercial losses, you are aware of, it is mostly illegal connections, theft, or the places where metering systems have not been installed. So introduction of metering and new water tariffs is required, as we've discussed earlier, to actually reflect the real cost. Because what happens is, I mean, most of the areas, the water that is being supplied to the mostly for residential requirements and all is subsidized, and people do not know the real value of water, which leads to a kind of psychological bias, wherein you tend to waste water because you don't think it is quite it's expensive, because just because you're getting a resource at a cheaper cost or a free, you tend to waste it. So it is important that you have real cost also being reflected into the tariffs. Then you may have to introduce consumption meters and pressure sensors, because this is something which empowers you to update your system conditions, detect gaps between supply and demand, depending on the granularity and localization of these meters and sensor installations. You can actually identify possible pipe bursts, leakages. This is another example wherein there was this program conducted here in Brazil between 2000 to 2008, where they have reduced the physical losses. So they took advantage of off-peak tariff systems, wherein these are some of the low-cost and innovative measures you should try in such conditions prevailing. But basically, if you see. Yeah, if you see here, the highlighted one, during low cost tariff period, what they did was to utilize that opportunity in storing that water into tanks, and then utilize those that water that you stored in tanks during the high tariff period. You can avoid the peak hour consumption costs, and then you can actually use it for your internal purposes. So this actually overall resulted in almost 22% reduction. 6% reduction in water losses and 22% increase in water tap connections. So overall, it's basically what are the final benefits for improving energy and water efficiency actions. One, energy savings. Two, it's about building resilience towards climate change through water savings. And then it's not just financial savings, but also resulting in reduction of CO2 emissions. So yes, I mean, we at C2E2 we are also we've almost completed developing a water tool for which can be used to assess individual components like transformers, motor pumps, motors, and also as a whole system for a water supply system. So this is a simple rapid assessment tool. The inputs are simple. The input parameters would be mostly about what is the volume of water that is being handled, what are the basic component details like efficiencies, do you have metering systems and control systems, what are the expenses and all. So once this all is taken as an input to the tool gives out one about the talks about different what is your existing efficiencies. It talks about is your efficiency as good in terms of the global standards, or do you have to is there any scope for improvement? If so, what are it also gives you to an extent the recommendations on what can be done to improve your efficiencies. And number 4 and the last one is about reflecting these efficiencies into potential cost savings and also giving you the payback periods. So yes, this is it from me on this topic. Thank you.
Hello, this is Xianli. I will give the last presentation this morning about also about water supply systems, the different options for challenges, options, and international support for taking actions. As Rahul's presentation is very detailed, so some parts of my presentation I will try to be brief. First, an overview of the global water withdrawal. Globally, our water use has been constantly increasing. In the past 100 years, the global water use has been a growth of 6 times, and it's still growing at around 1% per year. And largely, you can see in most countries globally, around 70% of the water withdrawal is for agriculture use, especially irrigation, and another 15% is for the energy sector, and 5% is for some other industry use, and around 10% for domestic use. And at the same time, in many countries, I think also in some African countries, a large share of the electricity comes from hydropower. So that's also a factor you need to consider about the close linkage between water sector and the energy sector. So especially water is heavy, it's dense. When you move it, it's require use energy, and that's why water supply system and the wastewater system is often use a lot of energy. And that's why also, as Rahul has presented, when you save water, you also save the energy use. And in most countries, also because of the quality of the water, to be able to use it, often you need to be some treatment before the use so that it reaches a certain quality, and after the use, you have to treat it again before it can be discharged into the natural system again. So that's also processes you need to use energy. For water planning, one issue is there are high uncertainties, especially because of climate change, because of population increase, and the different sources of water, and urbanization, economic growth. So this all affect the future availability of water. And also often water is also a tricky issue because it's shared by different regions, different countries, and different sectors for different purposes. So often you have to balance how to prioritize or protect the interests of different users and stakeholders. Also, energy production rely on water. That's why a lot of studies on this water energy nexus, and also it's related also to the food issue, the land use. So how you manage the water to balance, it's a very important issue. This water, energy, and land nexus in future development for many countries. And also because of the environmental issues, that urban water infrastructure is becoming more and more complicated because there are different fresh water availability issue and increased demand, and also the environment regulations. So that causes also population growth. So you have to think about when you do the water infrastructure, it's more often become more and more complicated. And with the water, also this treatment is increasing or intensifying because more strict standards and demands about what the water quality you can discharge into the natural system, and also for resource recovery in places that lacks water, and also climate change the impacts. So often that's also in terms of rainwater, how to make sure it's avoid flooding to different places. So in cities, generally, most cities have three main water flows. It's the rainwater, it's the water supply system, you have the water flow, and the wastewater discharging or treatment system. So these kind of three directions of water flows. And with the lack of water or water shortage, many countries are trying to explore unconventional water sources like groundwater, a lot of use, or it's just like a seawater desalination to get more water or sufficient water for the local supply. So one challenge in the water and the energy issues, such kind of projects as Rahul has recommended, in most countries, the water authorities and the energy authorities are different government agencies. Such kind of policy making often in isolation. They do not often they do not talk or work with each other. And the water prices, the energy prices are often established by some national government. There are different social targets in the price setting. And also often the water allocation modeling, when they do the projection for future water demand, this need a lot. Often water, when you project the future water demand, you need us to consider about when and the time and the space you need the water. Some places they may over the whole year they have generally sufficient water, but some seasons they lack water. And the energy modeling often they rely on that do not consider so much of the space issue. So in the planning, how to consider that both when you do the projection for future, consider about the energy impacts on water, water impacts on energy, so consider such issues in the policy making. Yeah, as I said before, that's also the policy, how the project investment, maybe the water utility company does not really work in isolation when they do the project planning. Do they consider about the energy issues? And when they, like wastewater treatment, they can also be a main important source of energy. But that kind of for planning such projects, the different government authorities need to talk to each other, work with each other to make such, to invest, to plan for such project and invest in it. There are additional water supply. Often in many places, the rainwater and the surface water flow are efficient to cover the local water demand, but often there's a water quality issue is a main problem, like water pollution. The water needs to be treated before it can be used. After use, it again need to be treated and be stored, keep clean and storage. And also the urban water flows, maybe sometimes you also have the issue like groundwater. In many places, there's an over withdrawal of groundwater that causes some also local environmental problems. So additional water resources can be available through three options. One is intensified treatment. So a lot of water, if you treat it properly, actually you can use it again for many purposes. And also increase the production from existing sources, and also it's water transfer. In some countries and regions, there are long water transfer projects using tunnels, channels to divert water from one region to another region. Generally, that's use a lot of energy, and the issue of also water loss along the way due to evaporation or leakage, as well as water quality problem. If it's open tunnels, often when the water reach after transport hundreds of kilometers, when it reaches its destination, maybe the water quality is not as good. It's again needs some treatment. So water energy and access in the traditional water planning system, you can see you need to consider both the water source and energy source during the planning. That's especially in countries or regions that rely a lot on hydropower. You need to think in the future planning and lack of water. How do you tackle these two issues together? To think about the planning process, the resource and the use, the future demand, to consider also the climate change, how to make use of the existing resources to sufficiently meet the society's demand or city's demand. Also, for when you do water planning, you need to consider use such Sankey charts to show where the water, you have to get the water and how it's used, which is different sources, or is the water is available, is seawater or is groundwater or surface water, and how you make it sure what are the different sources. You do have to have a clear idea where this water come from and how it's used, and think about future water resources, how much is available, how much you will need. So for such planning, one risk assessment, when you do such projects or planning for future water, you will need to consider how much resource is available and is it reliable, what's the risk of its change, and groundwater, surface water, or different sources, including seawater. So, and then you consider about the water quality, the guarantee rate, and these impacts on land use and the investment, the energy use, environmental impacts, and does it need some resettlement of some people? That can be also a main factor you need to consider, and also public acceptance. In some cases, even though treated wastewater can be clean enough, but people may not want to have it as domestic water. So also you consider vulnerability to climate change. So this is a WRI assessment. It's quite useful tool to assess what are the risks of your future different water sources. So the opportunities, how to realize the opportunities, it's thinking about this nexus approach. Nexus approach, not only think about water or only about energy. You think about their connections, energy, water, food, and climate change. These connections, and also integrated policy making, resource planning, and project investment project designing to maximize the benefits in terms of energy, water, and the natural resources. And another strong recommendation from various international studies and projects is acting now instead of waiting, because these kind of projects, the earlier you take action, the earlier you have the benefits. And finally, about the international support at different levels for such actions. The first is UN Water. That is coordinating the SDG 6 on global acceleration for water. So that is international support. Globally, the latest data is 2017, around $10 billion of support on development assistance for water and sanitation. Including almost 7 billion is in grants and 3 billion in some kind of loans, and also some other is in like the technical support. And also in 2017, the World Bank have this with some money from other donors launched this new initiative of global water security and sanitation partnership. So you can also get a lot of publication or resources from there, how they do it, and some technical support. And also this global water partnership, this year is 25 years. So it's an international network. It has also a lot of resources on how to do it, what different countries and cities are doing. The World Bank in 2014 have this 5-year study, Thirsty Energy. It's more on a lot on the water use of energy sector. So they are studying and seeing, identifying a lot of synergies and the trade-offs between energy development and water use, and also try to pilot some cross-sectoral planning to ensure when you consider the sustainability of both energy and water investment, and some tools how to do this. They also do some case study. They also find like a lot. It's easier to integrate water in energy projects than energy in water projects. So a lot that kind of lessons learned from different countries and regions. Finally, there are also online some different guidance tool like GIZ, this water and wastewater companies for climate mitigation. They have projects, also a lot of tools. And there are different city level studies and projects. So if you are an OECD study, World Bank study, and so if you are interested, you can look at those different sources and see how different countries, actors, they are doing it in practice, and what are the international supporting agencies are working on this area. Thank you very much.
Thank you very much, Ali, for your very thorough presentation. And now we will go to the Q&A session. And I would like first to start with you, Clara. And the question is, in how many years can we expect to recover the investment of replacing all the street lights in our municipality from conventional to LED bulbs?
Okay, thank you, Aris, for sharing this question, and for the person that posed that question, because it's actually a very good question. The reason why I didn't actually share the statistics on average return on investment is because they can vary substantially, case to case, depending on the energy price, on how many luminaries we're talking about, on what were the condition or the actual model of pre-existing luminaries, and many other variables. In many cases, it is recovered in less than a few years. or even less than a year. It should not take more typically than 2 to 3 years, but again, it depends on the systems you're implementing and what were the pre-existing conditions. It is, however, a very short period of time. That's the bottom line. And as I said at the beginning of my presentation, it is one of the lowest hanging fruits in terms of energy efficiency improvements on a municipal scale of intervention. So due to its cost effectiveness, and also it's quite easy to implement. In any case, if the person that's posing this question is interested in calculating what would be for them the return on investment, I think they can very easily calculate it for its own case using the C2E2 tool that I showed, and I highly encourage you to use. And it's completely free and available for all of you. And you can do that by clicking the link that I mentioned. I would really encourage you to do so. So yeah, hopefully this was useful, and yeah, looking forward to the next questions.
Thank you very much, Clara. Just I would like to mention that during the presentation, we sent through the chat function the links for those tools. So if you don't want to wait until we share Clara's presentation to access the link, please go to the chat function and access the tools from over there. Now, the next question is for Rahul. And Rahul, the question is, in case of long-term investment project, what is your comment on an appraisal for equipment energy efficiency with knowledge of future load expansion of heating and cooling without changing the capacity?
Thank you, Aris, for the question. It's a tricky question, I would say, but I'll try to answer or address an overview of the question here. Let me continue with the example that I was mentioning during the presentation. So there was this airport where we conducted energy audit, and it had built up terminal A, B, C over a large area. So they had this HVAC systems in place for catering to all these 3 terminals. But when you actually measure and assess the performances, it was found out that out of the 8 large chillers that were installed, only 2 were operating at any given point of time. And of those 2, it was loading only up to about 25 to 30% of the design capacities. So it was clearly showcasing that it was operating in part load conditions. So when you ask, or when we asked the operators and the management, it was informed that the systems were actually procured and set up for a period of 15 years. So they assume that after 15 years period, the X number of passengers would be using the airport. So for that reason, they have placed all these systems in place. So I do not have any comments on that part. And then if you look, you can just compare with another airport what we have come across. The approach was quite different. First, they have terminal A and systems belonging or sufficient for terminal A. So once they realize that in the next couple of years, the terminal A would be optimally packed with the passengers, then they move on to terminal B. So within that time, you would be installing newer equipments, newer technologies, and more efficient equipments in terminal B. And that likewise, they moved on to terminal C with relatively better equipments, because that is what the advantage what you get over the time frame. So what you see here is over the period of 7 years, I was observing these 2 airports. If it is with respect to the motors and all, then it doesn't make much of a difference, because there's incremental, very small incremental improvements that are happening, that have happened with respect to the motor efficiencies and all. But if you again look into the HVAC systems or the compressors or the chiller systems, there's been a huge improvement based on the area available, local technology available there. The specific power consumptions were back then available at about 0.68 and 0.7 for a water cooled chiller. And now it is like almost 0.6 and even 0.45. So even a 0.5 to 0.1 variation gives you a lot of difference in terms of energy savings, in terms of energy consumption. So answering the question about the knowledge of future load expansion, I think this was something which was mentioned in the question. So it is good that you at least have an idea of future expansion. Most of them do not have that idea itself. They randomly come up one day and say, yes, we are planning to expand. So this is something which is important, and it's good that you have that you have an idea of that you will be expanding in future. The next question that comes into the mind is, at what is the time frame? Will you be expanding within the next 2 years or 3 years or 5 years, or again, as I said in the first case, 10-15 years? So it again depends. The answer depends on what is the time frame here, and up to what quantum the expansion is, because there is always room for optimization by doing certain space improvements or changes in within the design or the infrastructure in place to for utilizing the existing capacities itself, installed capacities, like becoming more efficient, getting energy audit done, so that you know where are the key pinch points or power points where you can try to reduce the loads or improve the utilization capacities. So all this can be done within the existing capacities, as you mentioned, without changing the capacities. But if it is a drastic expansion, then I think it is always recommended to, it will always be recommended to go for additional capacities, again efficient capacities, because ultimately, as I was mentioning in the last presentation also, in the journey of becoming more efficient, we should not compromise on the quality of the personnel involved, or the product involved in the matter. Thank you.
Thank you very much, Rahul. The next question, I think it's mainly addressed to Xianli, because Xianli had the talk about the water treatment, and it's about the water treatment cost. And Xianli, the question is, how would the cost affect the whole scenario?
Thanks, Aris. Thanks for the question. Yes, the water treatment cost is in different countries. You have different systems. For example, here in Denmark, when we pay the fees for water, actually part of the fees also includes the wastewater treatment. It's not only just get the fresh water. So in all this wastewater, whether you get some payment from the consumers, or you have to entirely rely on the government. So that kind of cost also depends on what's where you come the income, and whether you have like different technologies. You get the treatment, like some heat from such kind of wastewater treatment. So the cost also vary a lot, different technologies, and also depends on what's the water quality of the water coming in, and what's the quality of the water after the treatment, that kind of requirements. So it's vary a lot, but in many cases, it's really important for the environment. If you think about future water supply, future environment, that's a necessary, definitely worthwhile from the social or environmental perspective. It's not only for the economic returns.
Thank you, Xianli. And now that you're online, we have another question. And the question is, how can we take the opportunities of enormous energy saving potential in urban water systems?
As I said, there's a huge, especially with the current situation of climate change and energy, and that's the impacts on the water and the future energy. That's definitely a lot of synergies when countries planning for their future sustainable development. They need to think about this close linkages between water, energy, and food. So that kind of some kind of mind changing or awareness raising among the policies to think about these issues. And also, as Rahul mentioned, prices of water and energy. If the price does not really reflect the cost, social cost, then people have no motivation to save it. So this kind of and again also integrated project planning. When you plan for a project, a water project or energy project, not just think about the water itself or the energy itself, also think about this future impacts from the other sector and its impacts on the other sector. So that kind of integrated planning, policy making needs to be placed to take the opportunities of water and energy, and a lot of opportunities for saving water and saving energy in the urban water systems.
Thank you, Xianli. Just I would like to mention, because we received many questions about the material, the presentations that are being shared. This week, we're about, until the end of this week, the recordings and the training material of the first 2 sessions are going to be ready. So please check on the link that is being presented on the slide, as you can see now, on the Copenhagen Center Knowledge Management System. This is the place that we will store all the information. And on another topic, also we received some requests about certifications. We will share with you a certification of attendance as long as you manage to attend at least 50% of all of the duration of the 5 e-training sessions. Our system can track how much time you spend on each session, so it's easy for us to make the calculation. But the certification, you will receive it from us, from the C2E2 email account soon after the end of the 5 training sessions. Ladies and gentlemen, finally, we come to the end of today's session. The next session will be held in 3 days. You will receive an automatic reminder 1 day and 1 hour prior to the broadcast. So I would like to say thanks to the panelists for the informative and interesting presentations, and to the audience for their active participation. We hope that the presentations will be beneficial for all stakeholders involved in energy efficiency. Thank you for your attention and wish you a good day from the sunny Copenhagen.